Remember this diagram? I explained that the parameters of a neural network are usually generalized with indexes like you see on the screen. Our network, however, has a fixed number of inputs and weights, 2 inputs and 2 weights. But a neuron can have any number of inputs. Suppose there are 5 inputs. We would have to create 5 variables for the inputs and 5 variables for the weights. Of course, there is a better way to do this. We can use lists for this. Let me refactor the code. I replace the weight variables with a weight list. The values are chosen arbitrarily. The next thing to do is to allow a list of inputs in the predict function. I need some loop through all the inputs and weights and sum their product. I use list comprehensions for this. As you can see, I have zipped the weights and inputs, then multiplied each weight times the input into a new list of products, and finally summed the resulting list. This is also known as the weighted sum of inputs. I can now pass all input elements at once. You probably have already noticed the duplicate code to calculate the weight updates. I'll make this more generic. At this point, the code gets a bit more complex. Let me show you why that is. The complexity is in the dimension of the weights deltas list we just created. Let me break it down. Inputs is a list of 16 training samples. Each input is a tuple of 2 elements. Errors-D is a list of 16 error derivatives. Let's take the first element from the zipped list. That would be this data. The values are multiplied element-wise. And here is the result for the first sample. The process is repeated for all samples in the training data. The result is a 2-dimensional matrix. The matrix contains the desired weight deltas for each training sample. A delta is some intended change to the weight. We now have a list of 16 weight deltas. Each row has a delta for weight 1 and weight 2. A second list is created with the deltas for the bias. So even with 2 inputs and 1 bias, we need to calculate a weights deltas matrix and a bias list before we can update the weights and bias. You probably already have a feeling this will get more complex as the network grows even more. And you would be right. Imagining and calculating with data in more than one dimension is not easy. It is one of the things that can make learning neural networks so difficult. I'll try to make it as simple as possible in the code. Let me remind you where we are in the process. Making the predictions is called feed-forward. Notice the use of the capital letters W and I. Without diving too deep into the math, just accept that W and I are not single values anymore, but lists or matrices. The cost is calculated just like before, after which the backpropagation starts. We have seen how to calculate the error derivatives for all training samples. We also just saw how to calculate the weights deltas and bias deltas. All we need to do is to update the weights and biases. Look at the deltas again. Calculating the average over the bias deltas list is easy. We already did this in the code. But how do we calculate the average over two columns in the weights deltas matrix? How can we do this? We transpose the matrix. This swaps the rows and columns of a matrix. Python can now easily calculate the average over each row. The result will be a list of two numbers, which is exactly what we need to change two weights. Let me show you how this works in the code. The selected lines update the individual weights. I will replace this code. First, I transpose the matrix so I can calculate the averages easier. I use Python's zip function and pass an unpacked weights_d list. Weights_dt is now a list of two rows with 16 elements each. And now I loop through the weights and update them with the transposed weight deltas. Okay, the code should now be able to work with any number of inputs. Let's see if everything still works. An error occurred. Ah, I see. I forgot to change the code for the test data. Let's try it again. Everything works again. We have successfully refactored the code to work with any number of inputs. And it is at this point where I can finally explain gradient descent. That was quite a change to the code. I want you to focus on the matrix of weight deltas and bias deltas. The weights deltas and bias deltas were averaged and used to update the weights and bias. In our network, there are three values: one to change weight 1, one to change weight 2, and one to change the bias. Together, these values are called the gradient. The gradient is a collection of deltas used to change all the weights and biases in a neural network. Here I show them as 3 dots, but you might have seen them written differently. In math, gradients are usually shown as a column vector, like this. It doesn't matter how we notate a gradient. All we need to know is that a gradient is used to nudge the weights and biases in a certain direction. And how is gradient related to gradient descent? Think of what happened in the code. An epoch is started. The error derivatives are calculated for each training sample. The derivative is used to calculate the gradient. The gradient is used to adjust the weights. A learning rate is applied to make small steps into the right direction. A new epoch is started and the process is repeated. The goal is to minimize the cost as far as possible. The cost does not need to be zero. In a system with real data, the goal is just to get it as low as possible. To summarize, a gradient is calculated based on the training samples and used to change the weights and bias. The cost descends, and the process is repeated. This algorithm is called gradient descent. And as you have already learned, since gradient descent is the average over the complete batch of training data, the process is called batch gradient descent. Look at the code. The weights deltas and bias delta are calculated separately. But all the values from both lists together form the gradient. The gradient is a vector that can have any number of elements. How do we visualize the gradient? A vector with one value is easy to understand. 2 values? No problem. 3 values? Still easy. But more than 3? How do we visualize this? My advice? Don't try. Don't you even try. Luckily, we have math. It does not have spatial restrictions like x, y, and z axes. A gradient can have as many dimensions as we need. I won't be able to show you more diagrams like this, because from here, our network will grow and its gradients cannot be visualized in 3D space anymore. But before we move on to complex networks, we need to talk about something else: classification. How this works, you will see in the next part.